Welcome to this explainer. Look, if you've been tracking the AI space, you already know the massive headache we face. Training these giant models is the ultimate bottleneck. Well, that's about to change. Today, we're unpacking a monumental shift in accelerated computing. We're going to look at how the NVIDIA Blackwell architecture is fundamentally rewriting the rules of AI training and data center efficiency.
All right, let's kick things off with a number that is just staggering. 208 billion. That is the number of transistors packed into a single unified Blackwell GPU. To actually pull this off, they used a custom TSMC 4NP manufacturing process. And to give you some perspective on the engineering here, this combines two reticle-limited dies, meaning they're literally the absolute maximum size a manufacturing laser can print, and connects them with an incredibly fast 10 terabyte per second chip-to-chip interface, so they function flawlessly as one unified GPU. So, you pack all that microscopic density together, and you have to ask, what exactly is powering this new industrial revolution? Because generative AI isn't just some software breakthrough, right? It demands a totally unprecedented approach to scaling up hardware. As we'll see, the answer lies in completely rethinking how these chips communicate, process, and scale.
To wrap our heads around this, our explainer today is going to cover a few key areas. First, we'll go inside the Blackwell GPU, then look at connecting the AI factory, mastering mixture of experts, the actual leap in AI training, and finally, massive scale and efficiency.
Okay, part one, inside the Blackwell GPU. Let's look at the foundational level. Now, this architecture comes in a few different flavors depending on what a data center actually needs. Take a look at the GB200 superchip column. It's the heavyweight here. It essentially takes the computational muscle and memory of the standard accelerators, like the B200 and B100, and just doubles them. It's rocking 416 billion transistors because it contains two of those massive GPUs, pushing 384 gigabytes of VRAM and an absolutely wild 20 petaflops of FP4 tensor performance. Moving on to part two, connecting the AI factory. Let's see how these build out an interconnected infrastructure. Say hello to the GB200 Blackwell's superchip. This beautiful piece of hardware is really the fundamental building block of the modern AI factory. It connects two of those high-performance Blackwell GPUs directly to an NVIDIA Grace CPU, and they communicate over a high-speed link that provides 900 gigabytes per second of bidirectional bandwidth. That incredibly tight integration ensures your GPUs are constantly being fed with data. But of course, what happens when you string hundreds of these together? Well, you hit a massive communication bottleneck. You can't have these incredibly fast chips just sitting around twiddling their thumbs waiting for data from their neighbors. So NVIDIA uses their 5th generation NVLink. This stitches the GPUs together with a mind-bending 1.8 terabytes per second of bandwidth. And when you scale that up, you get the ultimate result of that interconnect technology, the GB200 NVL72. This is a liquid-cooled, rack-scale design, packing 36 Grace CPUs and 72 Blackwell GPUs. Because of that NVLink tech we just talked about, this entire rack essentially acts as a single massive GPU. We're talking up to 30 terabytes of fast access memory and an NVLink domain offering 130 terabytes per second of low-latency communication. All right, part three, mastering mixture of experts. Let's look at the new software models. Before we talk raw training speed, we got to understand the software these systems are specifically built for. Mainly a technique called mixture of experts, or MOE. This approach takes extremely large, trillion-parameter AI models and chops them up into smaller, specialized sub-networks. This is absolutely huge for deploying complex systems where response time is everything. So instead of firing up the entire massive network for every single query, an incoming task gets dynamically routed only to the relevant expert subnetworks. This makes real-time inference lightning fast, and it makes training way more efficient because you aren't processing the whole massive model for every single data token. Which brings us to part four, the leap in AI training. This is where we see some truly unprecedented performance. When you combine that advanced mixture of experts routing with the massive scale of the NVL72 rack, you get a remarkable 4x faster training speed for large-scale models, like a GPT-MOE 1.8 trillion parameter model compared to the previous Hopper generation. This leap is heavily driven by the second-generation transformer engine. It uses new microscaling formats, including 8-bit floating point precision, or FP8, giving you high accuracy and way greater throughput during those grueling training runs. Now, you might be thinking, okay, but what if our enterprise doesn't have the full liquid-cooled NVL72 rack? Well, even with a discrete 8-GPU HGX B200 setup, you're still looking at a 3x faster training performance over the H100 standard. That means engineers are iterating faster, experimenting instantly, and shortening shipping cycles without waiting in hardware queues.
But here's the kicker. It is not just about training. Real-time inference throughput absolutely skyrockets. For that same massive 1.8 trillion parameter model, the GB200 NVL72 rack pumps out answers 30 times faster than the previous generation. 30 times!
And finally, Part 5. Massive scale and efficiency. Let's see how this architecture is flipping the script.
Usually, in the world of hardware, a massive performance jump means unmanageable power demands and spiraling costs, right? But Blackwell flips that entirely. Data centers today are totally power constrained, but compared to the H100, Blackwell delivers a 12x lower total cost of ownership and 12x lower energy use for these heavy real-time inference workloads. You are getting vastly more performance out of every single watt.
So how exactly are they pulling this off? Well, it's a mix of a few really smart technologies. First, moving to liquid cooling boosts water efficiency across the data center by over 300 times. Then, there's a dedicated RS engine, reliability, availability, and serviceability, that literally uses AI to predict hardware faults and intercept downtime before it happens. Throw in a dedicated decompression engine that speeds up database queries by 18x, and hardware-based confidential computing over NVLink, and you have a totally highly tuned, secure ecosystem. And if we peek just a bit down the roadmap to where this is all heading, we've got the upcoming Blackwell Ultra. Built specifically to accelerate the next generation of agentic AI, where AI agents are actively performing multi-step tasks, Ultra promises up to 50x better inference performance. So yeah, this architectural foundation still has immense headroom for the coming years.
As we wrap up this explainer, I want to leave you with a thought to ponder. For years, the sheer time and compute power needed to train a multi-trillion parameter model has been the ultimate barrier to entry. But with hardware like this effectively eliminating training queues and drastically slashing power costs, what incredible world-changing innovations are engineers and startups going to build next, now that the hardware can finally keep pace with their imagination? Thanks for joining me on this deep dive, and keep learning.